Welcome to the video for essential idea number 4 in our nuclear chemistry unit. Essential idea number 4 deals with monitoring and observing a sample of a radioactive substance decay over time. Some decay very rapidly, some decay over even millions of years, but they all follow the same mathematical model, that of exponential decay. The term we're going to learn about here is half-life. Every radioactive substance is designated with a half-life, and so we're going to pursue that. Okay, so we'll start with the graph here, and this is the most generic graph that you're going to see of this exponential decay. And I say generic because the x-axis is just labeled half-life. So we don't see it as 10 years, 20 years, 30 years. We don't see it as 5 hours, 10 hours, 15 hours. We see it as just number of half-lives, 1, 2, 3. And every radioactive substance has its own half-life that you have to consider when making this graph. And then it's also generic in that it just is labeled, hey, you're starting with 100% of your substance. So it's not saying that we're starting with 5 grams and watching it decay, or 1,500 atoms and watching it decay. It's just 100%. So let's work through the generic graph. So half-life means that when that time period goes by, whether it's 5 hours or 5,000 years, when that time period goes by, half of the radioactive atoms in that sample of radioactive substance will have transmutated. The other half won't have yet. That's seen visually in this graph up top, where you start with, it looks like 100 atoms and they're all shaded red. So let's say those 100 atoms are all radioactive. And when a half-life goes by, half of them have transmutated into whatever their product nucleus is. And so that's become the gray, and they're done now. They're now stable. But half of them, the other 50 atoms, are still radioactive. And so then another half-life goes by, again, be it 5 hours or 5,000 years or whatever it is for that particular element that you're considering, and half of those red ones remaining, half of those 50 still radioactive isotopes, half of those will decay. And they'll become gray, meaning stable, and then you're done with them. And then lastly, I guess to complete the graph, we have yet another half-life goes by, and half of the half now decay, and so you've got even fewer still radioactive atoms left in your sample. And so graphically, if we start at 100, and then after that first half-life, if half of those atoms have transmutated to the stable isotope and half are still radioactive, then you're left with 50%. And then during the next half-life, when the half of the half, or half of those 50% transmutate, you still have 25% left. And then you have 12.5% left. And then you have 6.25% left. So that's an exponential decay graph. And you're going to see that same shape all the time. The only thing that's going to differ is the actual x-axis, where you plug in what the half-life is, and the y-axis, where maybe you're starting with a certain grams or a certain number of atoms. The only other thing I want to focus on this graph, and maybe I'll even switch colors to do that, is an experiment that we often have you do in class that involves pennies. And so that penny flipping leaves a certain impression on students. And so what we would do in the classroom is we'd start with 100 pennies, and we'd put them on heads. And so it would look very much like this leftmost diagram here. So you've got 100 pennies on your tabletop, all heads, and we say, okay, those are some substance. You've got 100 radioactive atoms of that substance there. And then we say, okay, the half-life is 1 minute. So try to flip all the pennies in 1 minute. And then half of them, their time is up, and they actually transmutate to the gray circles, or to the tails, if you will. And the other half have flipped back on heads, so that indicates that they haven't transmutated yet. So that first minute goes by, and then you end up with a tabletop of pennies that looks like this. And then I think I said the radioactive were the heads ones. They're certainly the ones that are red in this diagram. So now take another minute and flip only the red ones, because the gray are done. They've now transmutated. They're not radioactive anymore. But flip the 50 coins that remain on heads, flip those, whoosh, and half of those are going to still land on heads and therefore still be, quote, radioactive, and half of them will have flipped to tails. That's now not radioactive, and you're done. And then your third minute goes by and you flip only those 25 red pennies there, and 12 of them are going to land on heads and still therefore be modeled as radioactive in this classroom experiment. You can never tell when any one particular atom is going to spontaneously decay, but the math model works if you're looking at a large number of atoms. So if we take a look at this atom on the upper left, that atom right there, well, my gosh, in that first half-life, that one transmutated, and then that stayed its stable atom. If you look at the second one in, that one went through 1, 2, 3, 4 half-lives, and that one didn't decay. So it's really a law of averages thing. That's what half-life is about. So if you take a radioactive sample and you hone in on one particular atom, you can never really say when that one's going to transmutate. But looking at a huge collection of them over time, the mathematical model of exponential decay fits. One final word on this. Just like if you had a penny and you were to predict whether it was going to flip the one penny, land on heads or tails, well, you couldn't really tell each time. But if you have 100 pennies, then you could, or through 100 flips, you could more accurately say that you're going to get 50 heads and 50 tails. Okay, so then the rest of this is just looking at the specific graphs for this. So let's delete that and let's find other graphs on here. So the only thing that starts to happen on these other graphs is they start to fill in for the half-life. So this first one is for carbon-14 that has a half-life of 5,730 years. This is the one that's used for dating antiquities. How carbon-14 works is a great research topic. And so you've got some amount of substance. They're starting with the initial amount. 5,730 years has to go by before you get only half of the remaining carbon-14. The other half is transmutated to nitrogen, and you're done with watching those atoms. Another 5,730 years goes by. You're now up to 11,460, and half of the half still have yet to transmutate. But now 3/4 of the atoms in your sample have transmutated into nitrogen. And this one is probably for a radioactive substance called technetium, specifically technetium-99, I think. It's got a half-life of about 6 hours. It's used in medical applications. So notice that they've filled in for the half-life here. It's still the same general shape. They're starting with the fraction of the original sample. So you've got your full sample at zero, but at time 0. But instead of having to wait 5,730 years for half of it to decay, you only have to wait 6 hours. So after 6 hours, half of your original sample is left and the other half is transmutated. And now you're down to half your sample. In the second time, half of the half has transmutated, and then half of the half of the half. That's why its slope keeps decreasing, but that's the classic shape of the exponential decay graph for radioactive substances. Okay, I think that might be good even with another graph in here. Let me just take a quick peek. Yep, I think it's more of the same. It's more filling in for specific half-lives, and it's filling in for specific amounts that you're studying them, and then watching the half and the half of the half and the half of the half of the half proceed. Okay, so for your research here, if you wanted, you could pick some radioactive substance, and particularly one that has an application for us, and talk about the substance, its radioactive half-life, and how it's used in its application. Thank you.